In this video, we are now going to have a look at the concept of electronegativity. So in order to understand what electronegativity is, let's just have a look at a covalent molecule. So I'm just going to choose hydrogen and its shared pair of electrons in there. So over here we have a H2 molecule and we have one covalent bond between them because we have a shared pair of electrons there. Now, if you remember, the center of each of these atoms, there's a nucleus, and the nucleus has a positive charge. The electrons here are negatively charged, so a covalent bond essentially is the attraction between the bonded nuclei, so the positively bonded nuclei with the negative shared pair of electrons in the middle. Okay. Now, in this case, because they are both the same atom, they're both hydrogens, they will have an equal attraction to the electrons in the middle. So these electrons here will lie right in the middle of these two nuclei, okay, because they both have the same attraction towards those shared pair of electrons. Now, if we have, for example, this is H2, the same thing would happen if we had O2, because both the atoms in O2 are oxygen. The shared pair of electrons, or the two shared pair of electrons in the middle, will lie exactly between those two oxygen atoms because both those atoms are the same. Same thing would happen with anything that's essentially diatomic. The electrons will lie right in the middle. Okay. Now this can change if those bonded atoms aren't the same. So if this bonded atom here was anything else, like, I don't know, chlorine, that was change this over here, those electrons there might not lie exactly in the middle. Okay, and this is where the concept of electronegativity comes. When we have two different atoms, those electrons might not lie in the middle. So if we now define electronegativity, so electronegativity is the attraction of a bonded atom for the pair of electrons in a covalent bond. I've just highlighted covalent because people tend to forget that part in the definition. So it's the attraction of a bonded atom for the pair of electrons in the covalent bond. So essentially, we're now going to have a look at the electronegativity of all the elements and see how they differ in their attraction to the bonded atoms, the bonded electrons. So in order to understand electronegativity, we're going to look at the Pauling's electronegativity scale. You don't need to know these numbers off by heart. If you are ever asked to analyse them, they will be given to you in the exam, but we're just going to have a look at how electronegativity changes. So first things that is worth noting, the higher the number on the Pauling scale, the more electronegative the atom is. So the more electronegative an atom, the greater attraction it will have on the bonded pair of electrons. So all of these have numbers on them. So for example, sodium 0.9, cobalt 1.8, sulfur 2.5, chlorine 3.0. So that's just the number, that's the Pauling's value that is given to them. As I said, you don't need to know them off by heart, but you do need to understand the trend that's going on over here. Hopefully you can see that as we go across the periodic table, so we go across any period, the Pauling's value increases. Okay, so as you can see, so potassium over here is 0.8. By the time we get all the way over here, it's 2.8. Noble gases, we don't tend to worry about them and their electronegativity. Some of them don't even have one because they don't take part in, they don't form compounds. And hopefully you can also see that as we go up a group, so not down a group, up a group, the electronegativity increases. So if it increases in that direction and increases going up, that should tell us that the element with the highest electronegativity, the element that's the most electronegative is fluorine. So fluorine has a number of 4, so that's the highest compared to anything over here. And after that, I'd say oxygen's quite electronegative, nitrogen and chlorine are also quite electronegative. Metals don't tend to be electronegative, okay, or they have a very small value on the Pauling's electronegativity scale. Also worth just pointing out, hydrogen over here is 2.1. It's not technically a metal, okay. So now that we know that, we can use the Pauling scale to identify what's going to give a covalent bond and what's going to give an ionic bond. Okay, sorry, bond here as well. So if the difference in the electronegativity, so the difference in the electronegativity value on the Pauling scale is 0, so let's say the difference is 0, that will tell us we have a covalent bond. So for example, hydrogen has a electronegativity number of 2.1. If it bonds with another hydrogen, because that is also 2.1, the difference between the two is 0, and that tells us that we are going to have a covalent bond between the two hydrogen atoms. Okay. If the difference between the two is 1.8 or greater, that tells us that we are likely to have an ionic bond. Okay, so let's now have a look at the scale. So over here, let's just have a look at lithium and oxygen. So lithium has a value of 1.0, and oxygen has a value of 3.5. Okay, so on the scale, the difference between them is 2.5. That is 1.8 or greater, sorry. That is 1.8 or greater, and therefore lithium and oxygen will give an ionic bond. Okay, if it has something between 0 and 1.8, that tends to give a polar covalent bond. I'm going to have a look at what we mean by that in a second. So if it's between 0 and 1.8, it tends to give a polar covalent bond, which we'll have a look at an example of that in a second. Okay, so this is just a way that we can predict what type of bond. As I said, this is just a way to predict it. It's not always necessarily going to be accurate. Okay, but if the difference between the Pauling values is quite large, so if it's 1.8 or greater, you will most likely have an ionic bond, and that tends to happen between most non-metals and metals. Okay, let's now have a look at what we mean by polar and non-polar bonds. So let's firstly start off by looking at a non-polar covalent bond. Okay, so let's have a look at a non-polar covalent bond. So an example of that is where we have hydrogen, so H2 molecule, or if we have O2. Another example of it is actually where we have a CH bond. I'll explain in a second why. A non-polar covalent bond is where the electron pair is shared equally between the bonding atoms. Okay, and that happens when we have two atoms that are exactly the same. So we say, because the electrons are being shared equally over here, so I'm just going to draw them in. It's not a divide sign, they are electrons being drawn in. Because they are being shared equally, they are found in the center of that bond, and we call that hydrogen bond there, not that hydrogen bond, the bond between the two hydrogens there, we call that a non-polar covalent bond. Okay, the electrons aren't leaning more towards one atom, they are right in the middle. Same thing happens in oxygen. Because they are the same atoms on either side, that the bond between the oxygen is classed as a non-polar covalent double bond. Okay. Another bond is carbon and hydrogen. Now they do have a slight difference on the Pauling's electronegativity scale. So hydrogen is 2.1 and carbon is 2.5. The difference between them is 0.4. But especially when we get onto organic chemistry, you do need to know that we class the CH bond as a non-polar covalent bond. Okay, so we assume that the electrons are being shared equally between the carbon and the hydrogen. Okay, let's now have a look at a polar covalent bond. Okay, so if a non-polar covalent bond is where the electrons are shared equally, A non-polar covalent bond, no, let me say that again. A non-polar covalent bond is where the electrons are shared equally. A polar covalent bond is where the electrons are shared unequally between the two atoms. So this happens usually when we have a greater difference in electronegativity between the two atoms. So let's have a look at a hydrogen and chlorine bond. Okay, so hydrogen on the Pauling scale has a value of 2.1 and chlorine has a value of 3. Okay. So the difference between the two is 0.9, so it's not enough for it to be an ionic bond. It is a polar covalent bond. So chlorine here has is more electronegative than the hydrogen, as it has a larger value on the Pauling scale. So what that means, it has a greater attraction. So the shared pair of electrons here, it has a greater attraction to those, and that means it's going to pull those electrons slightly closer to it. Okay, so if I just draw those electrons in, just for you guys to see, those electrons are going to be held closer towards the chlorine. And what that does is it polarizes the bond over here. Okay, as you can see, there's more negative charge over here than there is over here. And what that does is it creates a region of more negative here and more positive over here. And we show that by drawing a dipole. Now to draw a dipole, so the word that I've just used there is dipole, we say there is a dipole across this bond because the electrons are lying closer towards the chlorine atom than they are lying towards the hydrogen atom. To show that dipole, we use these symbols over here, so we'll have to have that somewhere and that another place. So this symbol over here that I've used is called a delta. Okay, so this is a lowercase delta. So this is a delta positive and this is a delta negative. So that means it's not an actual positive charge. The delta here just means it's slightly positive, and this one here means it's slightly negative. Okay, so given that the electrons are lying closer towards the chlorine, this chlorine has a slightly negative charge, and this hydrogen over here, because the electrons are far from it, we say has a slightly positive charge. And by drawing those symbols in with those atoms, we have shown that there is a dipole across this bond here. And because there is a dipole, we call this a polar bond. Okay, and because this dipole always exists, because the electrons will always lie closer towards the chlorine, we say that it has a permanent dipole. Okay, so there is a permanent dipole across this hydrogen-chlorine bond. Because chlorine is more electronegative, the electrons lie closer towards the chlorine. Okay, so anytime you want to show a dipole, you have to show a delta positive on one atom and a delta negative on the other atom. The one with the delta negative is the electronegative atom, and that means the electrons are lying in that bond, they are lying closer towards the chlorine. It's still a covalent bond, it's just an uneven one. Okay, right, let's now have a look at molecules that are polar. So we've looked at a polar bond. Let's now have a look at a polar molecule. Okay, so the first example I can think of is water. Okay, so if we look at just the bond, so let's have a look at whether we have a polar bond or not. Okay, so hydrogen is, so we know that oxygen is very electronegative and the hydrogen isn't. If we were to look at the scale, oxygen is 3.5 and hydrogen is 2.1. So as you can see, there is going to be a polar bond here. Because oxygen is more electronegative, I didn't complete the diagram, sorry, I should draw a lone pairing. Because oxygen is more electronegative, the oxygen holds the delta negative and the hydrogen holds the delta positive. So that means that the lone pair of electrons in this bond here lie closer towards the oxygen. And the same thing is going to happen across this oxygen and this hydrogen bond. Okay, so we have in this molecule, polar bonds. Okay, so we have a polar bond here and we have a polar bond here. I don't need to draw another delta negative on the oxygen, I just need to draw one, but there's a polar bond here and there's a polar bond here, so that means the electrons in both these bonds are lying closer towards the oxygen. What we can now do, so we've identified that water has polar bonds, we now need to identify whether water is a polar molecule, so whether overall this entire molecule is a polar molecule. Okay, we're going to look at another example later where there is a difference between the two. So in terms of the dipole, we've got a dipole here and we've got a dipole here. So I can show a dipole using an arrow with a line like that. Okay, so the area with the line over here, so this is the positive end of the dipole, the one with the arrowhead is the negative end of the dipole. So across that bond, the positive region is here and the negative region is there. I can do the same thing on this side, so the positive region is here, negative region is there. Okay, so both of these dipoles, as you can see, are acting upwards. Okay, they are not cancelling out. Okay, they're not cancelling out, all they're doing is adding to each other. Okay, so overall, in this water molecule, because those dipoles are adding together, so this region at the bottom is positive, this region at the top is negative, we can say that the whole molecule, I'm just going to draw straight through it, has a dipole going across there. So the positive region is down here, okay, and the negative region is up there. So there is a dipole going across the entire molecule now, because both of those dipoles add up, and we say that overall water is a polar molecule. Okay, so it has polar bonds, and overall it is also a polar molecule, and that's why water can act as a very good solvent for polar compounds. Okay, let's now have a look at another compound. So I'm going to look at carbon dioxide. Okay, oxygen again, very electronegative, and therefore you will have a dipole going across the carbon-oxygen bond. So in this case, oxygen is more electronegative, so the electrons in the bonds here are going to lie closer towards the oxygen. So this is going to have a delta negative. My carbon is going to be delta positive. Okay, same thing's going to happen here. So electrons in these bonds are going to lie closer towards the oxygen because oxygen is more electronegative. So I'm going to have a delta negative on my oxygen and a delta positive on my carbon. Okay, in terms of dipoles, I have a dipole across this bond, positive region here, negative region here, and same thing is happening here. So positive region here, negative region here. Now, as you can see, both these dipoles are moving away from each other, okay, in exactly the opposite direction. So imagine that we've got the central atom and there's two people pulling on it. Because they're pulling at the same kind of strength, because oxygens are the same, so pulling at the same kind of strength, that central atom doesn't move. Okay, so this is kind of a different way of looking at it, but essentially, hopefully you can see that these dipoles cancel each other out. Okay, because they cancel each other out, overall, this molecule here is not a polar molecule. So this molecule has polar bonds, and we can see that with the dipoles. But overall, this is a non-polar molecule because the dipoles cancel each other out. Okay, I'm going to show another example of that. And that is this compound here. So it's basically a carbon bonded to 4 chlorines. Chlorine is electronegative. Chlorine is more electronegative than carbon, so there's a dipole going across each bond. Our carbon is always going to be our delta positive, and all of our chlorines are going to be delta negatives. Okay, so there is a dipole moving away from the central atom for all of those. Okay, I'm just going to grab this. So imagine that these white ones here are our chlorines and the central one is carbon. Let's imagine, so they're all pulling at the same strength, okay? Because they're pulling at the same strength in opposite directions, we say that these dipoles here all cancel out, okay? Because they cancel out, that makes this overall molecule a non-polar molecule. So again, this one here is a non-polar molecule because the dipoles have cancelled out. And it's also just worth pointing out, it does still have polar bonds. So the bonds are polar, but the dipoles cancel out, overall making this a non-polar molecule. If I were to change that ever so slightly, I'm just gonna write the whole thing. If I were to change that ever so slightly, so all I'm going to do here is one of those chlorines I'm going to replace with a hydrogen. Okay. As we know, carbon and hydrogen is not a polar bond. Okay, so I only have a dipole going across 3 bonds now. Okay, so let's imagine that I've just changed one of these to that. Okay, so there's nothing pulling on this side. There's no dipole going across this bond. Okay, but there is a dipole going across these bonds. So these are all pulling. Okay, this one here is not pulling. So that means that overall the central atom is going to move, and therefore the dipoles haven't cancelled out. Okay, so over here, I only have 3 dipoles going on these bonds. Okay, I don't have a dipole going across this bond, and therefore this molecule here has polar bonds. And overall, because the dipoles don't cancel out, this is a polar molecule.